Hola, hope you're all enjoying your day. My name is Yevhen. I'm an Android engineer at justeattechway.com. Justeattechway.com is a major player in the global food delivery market, operating under various brand names across Europe, North America, and Australia. I work in the logistics department on an app called Scuba, which is for delivering orders in European market. On this slide, you can see me smashing it at my food delivery duties during the start of my employment. As they say, you need to deliver a few pizzas before you can deliver great code. And here it's me killing it at my first ever attempt at surfing just 2 days ago here in Lisbon. So as they say, you need to catch a wave, a few waves to deliver a smooth presentation. For a long time, our app looked like this, but we wanted to modernize it and address long-standing issues. Since our couriers in the field receive a variety of assignments on different stages of their itinerary, and considering the intricate states of a courier journey, it made sense to rethink how we want to communicate between the server and the client. So it brings us to the agenda. We're going to start by briefly discussing what server-sent events is and why we choose it as a solution for our app. We'll continue by finding out how to integrate them on Android, and then we'll touch on the heartbeat mechanism in SSE, which keeps the connection alive. We'll also cover connectivity recovery strategies, including making the solution reactive using Kotlin Flows. And then I'll explain our last sort of an ID technique, which we use to maintain a certain level of synchronization and avoids duplicates. Throughout the presentation, I'll share case studies to illustrate experiences. So as we mapped out our courier's delivery flow, we realized that the existing backend service was not flexible or scalable enough to meet our needs. The merging with other companies and expansion of business, and we needed to address long-standing issues. All of that just pushed us towards thinking about introducing a new, completely new backend service to support different business models and so on and states. So to support this transition, we decided to enable our app to receive automatic updates from the backend from the very beginning. So we needed to choose the best technology for that. Therefore, we conducted a spike ticket to evaluate technologies such as WebSockets, MQTT, SSE, and polling to find the best fit for our case, ultimately choosing SSE. But before I dive deeper, I would like to get a sense of your familiarity with the topic. How many of you have ever heard about the SSE or maybe worked with the technology? Could you raise your hands? So I see some of you are familiar, so great. However, I'll cover the basics for the rest who have never heard about it. So SSE is a HTTP-based solution where a client subscribes to a data stream from backend, allowing backend to periodically send messages through that channel. In our app, we needed a channel for one-way communication from server to client to provide updates about changes in courier's itinerary, various shift updates, and similar events. The sending all of these events is essentially initiated by the backend without need to send return messages. Therefore, we rolled out WebSockets and MQTT. Their bidirectional nature would have introduced additional complexity and redundancy for our purposes. This consideration was pivotal in our decision choosing SSE, along with simplicity of implementation and the built-in feature for event tracking, but more on that later. On a similar train of thought, to supplement this, I recommend checking out materials by my colleague and friend Mario, who is actually in this room today with us. He did an excellent job comparing WebSockets polling and server-sent events in his article, so you can learn more information through this barcodes. Now that we've laid the groundwork, let's go over the basics of getting server-sent events running on Android. For our implementation, we opted for the SSE library from OKHTTP because OKHTTP is a well-established, reliable, and actively maintained toolset. And the SSE library fits perfectly with other dependencies from OKHTTP, which we had in our project. Though we went for this option, there are other alternatives out there, most of which are also built on top of OKHTTP. To integrate the library into the project, you need to follow 3 simple steps. Add the SSE dependency, obviously, create a subclass of this class called event source listener, which serves as a callback for events like on open, on closed, on failure, on event during communication with the server. Then we need to create event source by passing their OKHTTP client request, and the event source is essentially a dedicated channel that stays open between your client and server, so you can receive live updates as they happen. Also, some tutorials recommend making an additional call to OKHTTP, as it's shown on the current slide. But during testing of our implementation with the backend, we discovered that this step is redundant since the create factory function makes the call automatically under the hood. Doing so would create a secondary subscription to the backend service, which is unnecessary. And SSE request typically requires adding a text event stream header, but even if you forget, the OKHTTP has you covered. It will add it automatically. So when you want to close your event stream, you just call event source.cancel, and it will shut down the connection. With that, SSE setup is complete. Fairly simple, right? Fortunately, we're in the Android subteam had this great advantage of using a great library like OKHTTP SSE. However, my colleagues from the iOS subteam weren't lucky in finding any viable solution for handling SSE on their end. As a result, they had to implement it manually. During the proof of the concept stage, with OKHTTP doing the heavy lifting behind the scenes, of course, we didn't give much thought to the finer details of how the connection is kept alive until the iOS team, during the same POC stage, ran into some challenges during this phase and realized importance of such mechanism as heartbeats. So heartbeats are essentially small periodic messages sent from the backend to the client to indicate that the connection is still active. These are usually very simple messages that don't trigger any real action on the client side. Without them, the connection might be considered not active or eventually closed due to timeout. Handling heartbeats is simple as shown on the slide. Actually, it's a slide code from iOS counterpart where it's implemented. While a library like OKHTTP manages it automatically, understanding the role of heartbeats is very important, especially if you implement the solution on your own. Likewise, in a multi-platform setup, let's say, to keep connection alive and to prevent app from crashing upon parsing. SSE is the backbone of our Scuba app. We rely on it to manage the entire app state. Because of that, keeping SSE connection open is really important. In our code, we make sure that connection stays active by monitoring factors like network connectivity, the courier's work status, and other key conditions, which are important for us. At the same time, if certain condition isn't met, we want to close the SSE channel to maintain optimal performance. This is where making the solution reactive becomes very useful. In doing so, we can observe changes in real time, ensuring that we reconnect when necessary and shut down the connection when needed. Since OKHTTP is fully callback-based, we wrap it in a callback flow, as shown in the current slide. This allows us to return a flow of type SSE state, which can be then easily chained with other operators to handle reconnections, errors, and other events in a reactive manner. We place the event source.cancel inside this await close block to ensure that the connection is properly closed when the flow either canceled or completed. So moreover, the callback flow gives us direct access to the field channel, which coroutine uses to send elements to. This channel can be referenced within the callback flow through the public field and then passed to our callback class as a constructor argument to previously created subclass of event stream listener. In this subclass, we emit events for each callback received. This approach lets us send specific events through the channel they happen, and representing different states of the app, like successful connection, an error, event received. With this setup, we've created a continuous Kotlin flow that can be subscribed and observed from other parts of the app. Remember, the SSE is our backbone of our app. So maintaining connection open is crucial. By creating observable sources like these ones for network connectivity, shift status, and other key conditions that SSE depends on, you can then just use combine function from the standard library to merge the latest values emitted by each flow. This approach offers an effective way to control the SSE channel dynamically, terminated in whenever any of these observables emit an update. The distinct until changed function could be used and very useful to prevent unnecessary triggers of the downstream of flows when the same value is passed downstream. Then you can apply, let's say, flat map latest to the value produced by the combine operator, enabling you to subscribe or unsubscribe from the SSE channel when needed. Next, create a state machine to collect expected events, processing them correspondingly. To ensure the system remains robust, especially in cases when their server may be down, or it's really crucial to implement retries. However, there is a mistake on this slide. A fixed retry timeout can actually worsen the situation. So basically, for instance, if 1,000 of user connects, tries to resubscribe at the same amount of time, it will only exacerbate the situation. Therefore, it's important and to consider such strategies as, for instance, exponential backoff, where each retry is delayed by an increased amount of time, spreading out the requests and reducing the server load. Additionally, if the connection cannot be reestablished after reaching the maximum number of retries, it's important to have a sort of a fallback mechanism in place. That could be a fallback endpoint or another solution tailored for your specific needs. As we talk about recovering the connection in negative cases, it's important to touch on another strategy we applied in our app, which we call last start event ID technique. As we drafted our solution, my team and I, we needed to address two other critical scenarios related to nature of SSE channel. Obviously, SSE channel is a hot stream. This means that it emits events in real time and does not replay them when there's a new subscriber. And first, we needed to wait to recover the app state in case if app is crashed, killed by the OS, or manually restarted, or encounters any other issue. When the app relaunched, it needs to communicate with the backend, which itself must query the database and re-emit the freshest event to ensure that the app stays fully synchronized and no critical updates are missed. Second, we had to account for desynchronization that could be caused by load balancing. The load balancing is a common backend practice. It's about spreading incoming traffic across multiple servers, so one server doesn't get really too busy. Obviously, to balance the load, our SSE service uses more than one instance of it. So there's a when there's a change in driver status, such as a new order, maybe shift update, corresponding record will be read from the database and re-emitted in an SSE event. Now imagine one of the instances that was continuously sending events goes down. So with that happening, another instance takes over. And however, if the first instance crashed unexpectedly, it might not have recorded its last sent event ID. And even if it did, there's no guarantee that the client will receive it. Potentially, this could lead to desynchronization between the client and the backend. To mitigate this, the backend needs a specific timestamp to query the database, fetch all relevant updates, and generate an SSE event. To ensure the correct sequence of events and avoid duplicates, we rely on something that we call the late storage ID technique, where the client is a source of truth. The backend assigns a unique ID to each SSE event, which is by default actually is not supported neither in WebSockets, and it's a whole different story in MQTT. When a new event is received, you check its ID, and this ID isn't just a plain string. It's a complex identifier containing timestamp and a whole load of different information, which you need when you encode it. You can then ensure proper synchronization. So obviously, when you receive a new SSE event, you apply a predefined algorithm to tailor to your use to retrieve that information from it. If the received event's ID is more recent than the previous one, then you process it. If it's kind of later in time than the last stored, you kind of don't process and skip it. So yeah, perhaps you'll also need to pass the last stored event ID with each new subscription to the backend service. This allowed backend to know exactly where to pick up and ensure that no important events are missing and client remains fully synchronized with the backend. So working on SSE brought both successes and challenges, some of which we've briefly covered today. One key takeaway, though, is to use detailed logging to remote services such as Datadog or so on. It's very crucial because during our rollout, we quickly learned that solid logs helps a lot in identifying troubleshooting problems between when two parties involved, like backend, and such as missing IDs and so on. So obviously, introducing SSE had a significant positive impact on business overall and greatly improved career experience and many business metrics, which I'm not gonna share today, unfortunately. And so yeah, big thanks for hanging out with me today. I wish you a great rest of the evening. If you have any questions, yeah, I'll be here for the next 10 to 15 minutes. I would prefer to talk in person before I'll be heading to catch my flight. So I'm leaving today. Thank you for your attention.